Hi everybody. So today I want to talk to you about the center of mass of a system, and this accompanies section 3.11 in matter and interactions. So first of all, there's a special point in a system or object, any system or object, and it's called the center of mass. And you can model the motion of the object about the center of mass. If you were to track the motion of the object, for example, of this wrench, which you see above, you can see that the hole in the end of the wrench where you might hang it on the hook, it's making kind of a helical path through the air. It's making some crazy little circles there. But if you were to look at the center of mass of the wrench, then its trajectory is much easier to plot. And if you were to model the wrench as a point particle, then it would be the center of mass of the wrench that you would want to track for the motion. Okay? The rest of it might look like it was moving in kind of crazy, chaotic ways, but the center of mass will track nicely. All right? So the system will also move as if an external force were applied to a single particle of total mass m located at the center of mass. All right? An unconstrained object, like this wrench here, on which there is no net force, will rotate or vibrate about the center of mass. So let's think about this for just a second. Let's say that we have a mass on a spring, okay? And then that spring on one end is attached to a wall or a ceiling or something like that. And the object vibrates back and forth with respect to that wall position, okay? So that's kind of a different situation than, let's say, if you had a mass 1 and a mass 2, and then those things were connected by a spring. Now when the object would be vibrating, this net object, which consists of object 1, object 2, and the spring, then what's going to happen is the objects are going to vibrate about the center of mass. So it's no longer the attachment point of the system with which you would think, right? Now the objects are going to vibrate about the center of mass, okay? And if it were a free object, let's say that we took our springs with the masses there, and you tossed it into the air, then it would do a flip to flip, right? And the flip to flip would be about the center of mass of those two objects, okay? One way to visualize where the center of mass might be is it might be a balance point for the system. So like this bird here, this is a really popular physics demo. I have one for my kids too, for example. So this bird, its wings stretch forward and it's weighted, okay? So it's weighted in the front and the back. And then you can balance the bird on this little beak. So that's the balance point. So that represents the center of mass of that system. So if you can think of maybe balancing an object on a pivot, where would that object balance? That's the center of mass. For a person, for example, the center of mass might be close to the hips, right? If you were going to do a lift on somebody, you would lift them right here, right about their hips, and then they would extend their arms and their feet in all directions. So that's their balance point. So if the object isn't symmetrical, you can determine where the center of mass is by balancing on a pivot. Of course, if the object is symmetrical, like let's say that it's a solid cylinder or something like that, then it's pretty easy to guess the center of mass because it's going to be on an axis of symmetry if it has uniform density. Okay? If you have point masses, which is what we're going to be dealing with at first in Chapter 3 of Matter and Interactions, our textbook, then you would find the center of mass using the following equations. Here I've labeled xcm, ycm, and zcm as the x, y, and z coordinates of the center of mass of an object. So the x center of mass of the object would be the sum of each one of the masses in the system, mi, times its x coordinate xi. And then you would divide that by the total mass of the system, which I call big M. The y center of mass formula is also similar. The sum over I of mi times yi over big M. And ZCM is the sum over I of MIZI over big M. So here, the I is just the indicator in the summation, and you would sum over however many objects you'd have. So for example, for this little simple system here with two objects, you have M1 and M2. So it would be a sum over I from I is equal to 1 to 2, right? And you would have M1 x1 divided by M total plus M2 x2 divided by M total. All right? So if you wanted to write that out in full vector notation, then we'll call the position vector for the center of mass r sub cm. And then for a system of particles, RCM would be 1 over the total mass, big M, times the sum over I of MI RI, where RI is now the vector, right, the position vector, and not just one coordinate. So RI would be the position of the ith particle. In unit vector notation, that would be RI is equal to xi I hat plus yi j hat plus zi k hat. Now you can also talk about the velocity of the center of mass of a system. And you can do that by just taking the time derivative of the center of mass position. Okay? And then we take the velocity, we find the velocity of the center of mass. So mathematically that looks like, here we're going to call the velocity of center of mass v sub cm, right, for center of mass. And then that would be dr dt, where r is the position of the center of mass. Okay? So that would be m1 dr1 dt plus m2 dr2 dt plus m3 dr3 dt, and you keep going over the whole summation, right? And then that would be divided by the total mass, big M. Now, of course, the dr1 dt, that would just be the velocity vector for object 1. And so you could write that expanded as equal to, the velocity of center of mass would be equal to m1 v1 plus m2 v2 plus m3 v3, so on and so forth, divided by the total mass of the system. So you might notice that this m1 v1 plus m2 v2 plus m3 v3, well, that's just the total momentum of the system. You're summing up the momenta of each of the individual constituents of the system, right? So that's the momentum of the system, which I'll call P sub sys here for system. And so that means that I can express the momentum of the system as the total mass of the system, big M, times the velocity of the center of mass. All right? So that's one convenient way to do it. Now, in previous lectures, we talked about the conditions for the conservation of momentum. The condition is as follows. If you have an isolated system that has no net external force acting on it, then momentum is conserved. And that's expressed mathematically as the sum of all the external forces F would be equal to delta P over delta T. And that would have to be equal to 0. So that would mean that delta P was 0, which means the momentum doesn't change for the system. The initial momentum of the system equals the final momentum of the system. But one thing that you really have to keep straight in your head is be careful how you define your system, and make sure that you understand all forces that are acting on that system and whether those forces are internal forces or external forces. You can have conservation of momentum if you have internal forces. Let's say that you have a body 1 and body 2 and they collide and bounce off each other, okay? There are forces acting there, right? So there's the force from the collision of body 1 on body 2, right? But that collision causes an internal force to the system if body 1 and body 2 are colliding. So any internal forces are okay. It's external forces that you've got to be careful about for conservation of momentum. I'd like to emphasize that by doing this example problem and discussing it a bit more. So this is problem number 45 in matter and interactions. Let's read it together. 2 rocks are tied together with a string of negligible mass and thrown into the air. At a particular instant, rock 1, which has a mass of 0.1 kilograms, is headed straight up with a speed of 5 meters per second. And rock 2, which has a mass of 0.25 kilograms, is moving parallel to the ground with a speed of 7.5 meters per second. So what's the total momentum of the system consisting of both rocks and the string? And what's the velocity of the center of mass of the system? Okay, so let's go through and go ahead and solve for what the problem asks us to, and then let's go a step further and think a little deeper about the problem. So here we go. So just like any physics problem, one of the first things that you're going to do is list out all your knowns. So the mass 1, that's a known, it's 0.1 kilograms. Mass 2, 0.25 kilograms, that's a known. And V1, okay, it said that the speed was 5 meters per second and the direction was straight up. So using the convention that we've been using here, where y-axis is up-down, right, and the horizontal plane is xz, straight up would be plus 5 meters per second in the y direction. So V1 would be 0.50 meters per second using our standard notation here where the triangular brackets indicate a vector, okay? So 5 meters per second up would be plus 5 in that y component. Now V2, it said that it was traveling 7.5 meters per second horizontally, okay? So I'm going to define, just pick a direction, okay? So I'm going to pick the X direction here for the horizontal direction. Could have been Z, oh, that would have been okay too, but I picked X. Why not, right? You can always rotate your coordinate system if you want to. So here, that's 7.500 meters per second for the velocities. So those are our knowns, okay? Now, the first thing it asks is, what's the total momentum of the system? The total momentum of the system would be the sum of the momenta of the constituents. And so, of course, since momenta is mass times velocity, I would just do m1 times v1 plus m2 times v2. So that's what I'm doing here. 0.1 kilograms times 0.50 meters per second plus 0.25 kilograms times 7.500 meters per second. When I multiply through and then add those vectors in a component fashion there, I end up with 1.875, 0.50 as my vector components for my momentum, and of course the units are kilograms meters per second. Alright, so done, no problem. That's the total momentum, which is the momentum of the system. Alright, now, next thing it asks is, what's the velocity of the center of mass? Well, we already defined the momentum of the system is equal to the total mass times the velocity of the center of mass. So, since I have the total momentum, which is the momentum of the system, I can just divide that by the total mass of the system and end up with the velocity of my center of mass. So, P sys divided by m is equal to the velocity of the center of mass. Fine. So that's 1.875, 0.50 kilograms meters per second divided by the total mass, which is 0.35 kilograms, if I add together 0.1 and 0.25 kilograms. Okay? So, doing that division to each component in turn, I end up with a velocity for the center of mass of 5.4, 1.4, and 0 meters per second for its components. Alright? Now that's all the problem really asked me to do. It asked me to find the total momentum of the system, and it asked me to find the velocity of the center of mass. Great, I've done that. But now let's think just a little deeper about that. So, our system is rocks and string. What forces are acting on this system, right? If we let this thing continue to go through the air, what forces would be acting on it? Are those forces internal or external forces? And would momentum be conserved here? Okay? So, the problem says that you've got two masses tied by a string and you throw them into the air. So what possible forces could be acting on that? Well, we're here on Earth, so it's going to feel the force of gravity, isn't it? So that's one. It doesn't say anything about neglecting air resistance. So maybe you have to think about air resistance too, right? And then finally, you've also got to think about the tension in the string. That's definitely acting to keep the rocks tied together, right? So they're whirling around each other, maybe they're going through some crazy path in the air and rotating, okay? And that would stretch the string out, which would cause a tension in the string, right? Okay. So now let's think about some of the other implications here. Are these forces internal forces or external forces? Okay? The problem tells us that we are to define our system as the rocks in the string. So that's our system. So then the question is, do those forces come from within the system or outside of the system? If they come from within the system, then they are internal. And if they come from outside of the system, then they are external forces. So here, gravity and air resistance. What causes those forces? Gravity comes from the attraction of the rocks and the string to Earth. So since that's the case, then that means that the force is caused by Earth, which is external to the system that we have defined. Okay? So gravity is an external force. Air resistance comes from the air, and we haven't included that in the system too. Boy, what a hot mess that would be if we tried to do that. Okay? So let's say air resistance, also external, because it's coming from the air molecules which are outside of the system, which is rock plus string, right? The air molecules are colliding with the rock and the string as it flies through the air. And those little tiny collisions, there's a whole bunch of them, that causes the drag. Okay, finally, tension. Tension is internal to the system. We have defined the system as the two rocks and the string, right? And so what happens is if you have the rocks being pulled apart by maybe centrifugal forces of the things flying around one another, right? Then what happens is maybe rock 1 pulls on rock 2, and they do that via the tension in the string. So that makes tension internal to the system. Okay, so here's the question. Would momentum be conserved? No, right? Because there are external forces. Gravity and air resistance are external forces. And so, for that case, no momentum conservation. And if you think about it, this makes sense. If you throw something through the air, it goes through generally a parabolic trajectory. You've given it some initial momentum, kind of maybe up and to the right or whatever, right? Now, its speed changes, okay? Because the y component of the velocity decreases as it goes up till it reaches the peak of the motion where the y component of the velocity is 0, and then it starts to increase in magnitude again as it goes back down, okay? So the y component of the velocity is changing, but the horizontal component of the velocity, that stays constant. That means that the momentum of that body changes as it flies through the air. So that's definitely a case where momentum is not being conserved because there is an external force acting on it, and that external force is the force of gravity, okay? Now, let's put our heads in a space where instead of rocks flying through the air on planet Earth, right, we've taken these rocks, which are tied together by a string, and we are in outer space somewhere and we sling them, okay? Now, in that case, momentum of the system would be conserved once we let go, right? Because the only force then would be the force of tension on that string. And that's internal to the system of the two rocks. In other words, rock 1's pulling on rock 2, rock 2's pulling on rock 1, but since the system is rock 1 and rock 2, we're good to go. Internal forces only. So a tension there would not be a problem. Now, when would a tension be a problem? Okay? A tension would be a problem if it's attached to something external to the system. Okay? So if you had a rock suspended from a string on planet Earth that was tied to a wall, maybe, or a ceiling, in that case, you'd have to consider the building or whatever it's attached to external to the system. And then you'd have yourself maybe a pendulum. You'd pull it to the side, you'd let it go, and it would swing back and forth, right? Okay, so it's tied, and so you can't really consider that external anymore, or internal anymore. Okay, so it can be more complicated when you think through it, okay? But you have to really make sure that you understand when a momentum is conserved and when it's not. If there's forces external to the system that you have defined, momentum is not conserved. If there's only internal forces, in other words, forces between objects within the system, you're good to go. All right, hope that helped, and I'll see you around.